All right. Good morning, folks. Welcome to our 7.4 lesson. This is on finding minima and maxima using Lagrange multipliers. Okay. And so we've taken a look in 7.3 at another way of finding maxima and minima. All right, so that would be important to go back to 7.3. I know it's been a little bit since we had our review and we had an exam, but if you don't remember about minima and maxima, you can go back to the 7.3 notes and lecture, okay? Today, we're going to be focusing, however, on finding these maxima and minima using a different technique, okay? So this different technique is called Lagrange multipliers, and we are going to spend most of our time looking at using the method of Lagrange multipliers to solve optimization problems with one constraint. Okay, so the key here is that we're really going to be focused on the one constraint. We are going to do an example on two constraints, but I'm actually going to turn that into a separate video. So if you're interested in that, that'll be like a part two. And if not, then you can stop after part one. Okay, so video part two, we'll talk about the two constraints. But as far as the scope of what we're going to cover in our class in terms of the homework and the test, we're going to be looking at just one constraint. Okay. All right. So let's start with this motivation question, okay? A rancher wants to construct two feeding pens of the same size along an existing fence. If the rancher has 720 feet of fencing material available, how long should the length and width of the feeding pens be to obtain the maximum total area? So this looks a lot like some of the questions that we've seen in section 7.3, where we're looking for a maximum amount of something. But I think what we're going to do is we are going to apply what we know in 7.3, and even rewinding a little bit to what we did in the Math 121 class, because this is a problem that we have seen or have seen some variation of this at some point. Okay. And so in general, when you see these word problems, it's really nice to start off with a diagram. And what I mean by that is don't just draw a diagram, but also label it with any of the important information that you have. Okay. So I'm going to go ahead and draw two pens, right? And they're divided. And one of those sides is already an existing fence. Okay. So in particular, this side that I'm going to highlight with the yellow, there's already a fence there. So I just need to build 1, 2, 3 of these and one of these ones. Okay. Now, I also want to kind of label the different sides here. So it doesn't really matter what letters you use. You could use length and width. I like to use X and Y because the X's for me are usually the horizontal, like the X axis, and then the Y's are usually the vertical because of the Y axis. But what that would look like is I'd have Y here, Y here, Y here, and then this whole other side we're going to label with an X, okay? And from here, okay, I can actually write some equations. All right, so I call this an equation brain dump. And what I like to do is to go ahead and come up with all the equations that I might use with this diagram and the wording from the question, okay? So I know that I'm looking ultimately for the maximum total area. And so if I'm looking at the area of the pens, okay, I know that that area is going to be X times Y because I have a rectangle, okay? So that might be the more obvious equation, but the idea that we only have 720 feet of fencing material, that actually helps us come up with another equation, okay? In particular, this side plus this side plus this side plus this side should equal 720, okay? So I can write that as X plus 3Y equals 720. All right, now I think these two equations should be enough to help us figure out the maximum situation here, okay? So let's go ahead and use derivatives to help us out, okay? All right, so before I get to the derivatives, what I'm going to do is I'm going to take this equation, a equals yx, and I'm going to go ahead and turn it into an equation that only has one letter. And the way I'm going to do that is I'm going to use this equation here, the second one we came up with, to help us substitute, okay? So let's look at this equation for a moment. X plus 3y equals 720, okay? Now, x plus 3y equals 720 is the same thing as saying x equals 720 minus 3y, right? I can just subtract that 3y to the other side. And what's really nice about that is then everywhere I see an x in the area equation, I can replace it with 720 minus 3y, right? And so that's going to give me a new area equation of 720 minus 3y times y. And now I'm going to go ahead and distribute here, and that's going to give me 720y minus 3y squared. Okay. Now, this is my area formula. This is the one that I want to find the maximum of. And a few things we might notice here. I have a y squared. That's going to be like a parabola, but it's also negative y squared. So my parabola is going to look something like this. And I could find the maximum by finding the vertex. That's one way to do it. But maybe we also remember that if we have a parabola, that at the vertex, the slope is actually equal to 0. And the cool thing is slope is the same as derivative. And so what that allows us to say is that if we find our dA, dy, and set it equal to 0, we should be able to find out where that maximum is, okay? So I'm going to go ahead and take a derivative. dA dy equals 720 minus 6y. And I want to go ahead and set that equal to 0 because I'm looking for, maybe this is another familiar word, a critical point. Okay? All right, now no quadratics here, so no factoring. I'm just going to add the 6y to both sides. And I'm going to divide by 6, and I get y equals 120. And I'm going to include the units because I want to make sure that I know what I'm measuring, okay? So what this tells us is that the y part of the fencing, this piece right here, is 120 feet. It also tells us this is 120 feet and this is 120 feet, okay? Now we have to find our x value, and it turns out that that green highlighted equation is going to be really helpful because now we can say x equals 720 minus 3 times 120. So like whatever y value we got, we now plug that back into the equation, and we'll get 720 minus 360, which should give us 360 feet. All right. So this question, remember, is asking us how long the length and the width are. So I believe we found that, right? We found x to be 360 and y to be 120 feet. But then it also asks us to find the maximum area. So we're going to stick both x and y values back into the area equation, and we can go from there, okay? So step 4, we're going to answer our question. All right, so 360 feet by 120 feet are the dimensions. And if we multiply those out, we get an area of, I think, for that 432,000 square feet. Okay. So that's how much we can fence in if we are looking to construct those two pens along that existing fence. All right. So maybe this is something you remembered from Calc 1, maybe not. Either way, it's a good review of some concepts that now we're looking at derivatives and remembering how those can help us find certain things, okay? Now, I think the key part in all of this mess was really this take a derivative, set it equal to 0 part, okay? That's going to be a concept that now we're going to use when we look at functions that have more than one variable, okay? All right. So let's take a look at number 2, okay? Or part 2, Lagrange multipliers. So it turns out that we have this theorem, okay? For this method of Lagrange multipliers for functions of two variables, it turns out that we can find the maxima and minima with whatever constraint we have using a system of equations, okay? Now, I don't want to go too much into the formula right now. I think it'll actually be easier if we kind of do it, and then you can look back at the formula later, okay? But one key term I do want to highlight here is we have a constraint function that we're now going to call g of x, and in particular, that g of x needs to be equal to 0, okay? All right. I think we've seen this problem before. A rancher wants to construct two feeding pens of the same size along an existing fence. If the rancher has 720, this is supposed to be a 0, 720 feet of fencing material available, how long should the length and the width of the feeding pens be to obtain the maximum total area, and what is the maximum area? All right. So what we're going to do now, we're going to do the same problem we just did, but we are going to use the method of Lagrange multipliers, okay? All right. So here's how I like to set up for Lagrange multipliers, okay? What I like to do is I like to find my f comma xy equation and my g of xy. Okay, this step is going to be pretty short, but it's important that we find the function we want to minimize and our constraint function. Okay, so the function we want to minimize, well, that is our area, right? Or sorry, in this case, we want to maximize. So what do we want to maximize is the area. And the area formula for a rectangle is x times y. Okay. So last time I had called this A, but now this time I'm saying f of xy. It's okay to have two letters as an input. All right. Now let's find our g of xy. Okay. And our g of xy, it comes from the perimeter part, all right, where we have two feeding pens of the same size along the existing fence, and we only have 720 feet of fencing. So we have 3y plus x equals 720. Okay, that's the same equation that we had from before. But if we look back at what I highlighted earlier, I said g of xy has to be equal to 0, okay? And right now, I have g of xy equals 720. So this is not technically our g of xy, but we can make it our g of xy by doing one very simple thing, where we take 720x and we subtract it to the other side, okay? So let me make that modification. G of xy equals 3y plus x minus 720. Okay. With this minus 720, now it equals 0, and this is the g of xy equation that I want to use, okay? And I'll also box off the f of xy because that's the other equation I want to use. All right, so we find our f of xy, we find our g of xy, all right? And after that, now we get to do this part. We're going to find our partials, okay? But if you look, all of these partials are like capital F, and we only have lowercase f and lowercase g. So like, where does this f come from? It comes from here. F of xy lambda equals f of xy plus lambda g of xy. I know that looks like a lot of letters, but we're just going to plug in what we have and see what happens, okay? So, step 2, let's find our f of x, y, lambda, right? And that's a capital letter F, so it's important that we distinguish this in our brains, okay? I'm going to copy down that formula, f of xy equals f of xy, like lowercase f of xy, plus lambda g of xy. And then everywhere I see a f of xy, I'm going to put x times y. And everywhere I see a g of xy, I'm going to put this 3y plus x minus 720. I'm literally going to make a substitution, okay? So I get f of xy equals xy plus lambda times 3y plus x minus 720. Okay. Now I'm going to go ahead and distribute this lambda. And I want us to keep in mind that lambda is a number. Okay. Lambda is a number, and it's going to be a number that we're going to find. And finding that number will then help us find x and y. Okay. So let me distribute here. F of x, whoa, f of xy equals xy plus 3 lambda y plus lambda x minus 720 lambda. Okay. All right. So let's kind of go over what we have so far. So we found a lowercase f of xy and a lowercase g of xy. Then we use those two to find your uppercase f of xy lambda, okay? Lambda is a number, and that's important because in our next step, we are going to find our partials, okay? So we want to find fx, fy, f lambda, and we're going to set those all equal to 0, okay? So step 3, we're going to find fx, fy, and f lambda. Okay. So if I look at my equation, I want to take a partial with respect to x. That means everything else is considered a number. So fx equals, let's see, the derivative of xy will just be y. The derivative of 3 lambda y will go to 0. The derivative of lambda x is plus lambda, and the derivative of negative 720 lambda is 0. So my first partial, fx, is just y plus lambda equals 0. I'm going to do the same thing. I'm going to find fy and f lambda. So fy. Okay, we go back and find those partials. The derivative of xy is going to be x. The derivative of 3 lambda y is going to be 3 lambda. And the derivative of lambda x minus 720 lambda is 0. And I want to set this equal to 0. All right, we got one more partial to find. We're going to find our f lambda. Okay, xy, going to go to 0. 3 lambda y is going to go to 3y. Lambda x is going to go to x, and minus 720 lambda is going to go to minus 720 equals 0. Okay. All right, so I found my fx, my fy, and my f lambda. And now what I'm going to do is I'm going to take my fx and I'm going to solve for y, okay? And I'll tell you why we're going to do that in just a moment. All right, so and step 4 is we are going to solve for x, y, and lambda. Okay. Now, I'm just going to give you a heads up that when we solve for x, y, and lambda, it is going to be some kind of algebra. And the algebra is going to be different from problem to problem. And so I think the hardest part here is really about being flexible in your brain about what methods you might want to use. Maybe you do some substitution. Maybe you do some elimination. It could be a lot of things, and we need to be willing to go with it. And I know that's maybe the worst thing I could tell you the day after our first test, but I just want us to know that like it's going to involve a lot of algebra techniques. And this is where you need to really think about like all of the algebra skills that you've learned in the past. Okay. All right. So I'm going to go back to my fx equation. I had y plus lambda equals 0. And I'm going to go ahead and solve for lambda. So lambda equals negative y, right? I just subtract that y to the other side. Okay. Now, here's what I want to do. I'm going to take the x plus 3 lambda, okay? And that equals 0. And when I take a look at this one, I actually see that 3 lambda equals negative x, right? Same idea, I just subtract the x from both sides. But here's what I want to do, okay? So now I'm going to take the lambda that I have from here and the 3 lambda that I have from here, and I'm going to plug it into my f lambda equation. All right, so my f lambda equation was 3y plus x minus 720 equals 0. And so everywhere I see a x, I'm going to put a negative 3 lambda. Okay, so I can actually divide by -1. And everywhere I see a y, I'm going to plug in a negative lambda. Okay, so this is going to give me 3 times, instead of y, it's negative lambda, plus instead of x, it's negative 3 lambda. Okay, so this negative lambda's from here. And the negative 3 lambda is from that x value. And I'm going to add that 720 to the other side. Okay. Now I have negative 3 lambda minus 3 lambda equals 720. And I can combine those to make negative 6 lambda equals 720. And then when I divide by 6, I end up with lambda equals negative 120. Okay? So I've found my lambda, but what this means is I can use that lambda to find y, and I can also use that lambda to find x. Okay? So my lambda is negative 120. So y equals negative lambda, which is negative 120, which is 120. Okay? And now we know this is 120 feet because we're looking at the same like setup as we had on the last problem. And we said that x equals negative 3 lambda, and that's negative 3 times negative 120, or 360 feet. Okay. And so what this shows us here is that y is 120, x is 360, and those are the same values that we got last time using this method. Okay, so this method here is called the method of Lagrange multipliers. All right. In fact, this lambda that we've been seeing, that's the Lagrange multiplier. Okay. It's a pretty cool technique that allows us to just kind of like work with things and not have to get it in terms of a single variable, right? Like back here, I know this is strictly less ink, but what we had to do is create an equation that only had y's in it, and that's how we were able to find a derivative. But now that we know how to do partial derivatives, that allows us to look at things like Lagrange multipliers, okay? So quick checkout in the audience. Any questions so far, or how we doing? All right. So let's take a look at number 2. Okay. So not all of these will have a word problem associated with it. I wanted to kind of like strip it down to just the function and the constraint and use that to go through the process one more time. Okay. So a lot less words here, but this says minimize this function subject to the constraint x plus y equals 10. Okay. So in order to make the thing in the yellow our g of x, we'll have to set that equal to 0, which means I'm going to have to subtract that 10 to the other side. Okay. Now we're going to go through all the steps, but I just wanted to kind of get us to preview that idea a little bit. Okay. So step number 1, we're going to find our f of xy and our g of xy. Okay. Now, f of xy, we don't really have a lot of work to do this time because they gave it to us. X squared plus y squared. That's it. And our g of x, well, we do have to do a little bit of work, but we know g is like related to the constraint. And so we want to take this x plus y equals 10, and we're just going to subtract the 10 so we can make that g of x equals 0. Okay, so x plus y minus 10 equals 0. All right. After we find our f of xy and g of xy, we're going to find our capital F of x and y and lambda. Okay. And so when I do that, I get f of x, y, lambda equals my f of x. That's the f of x, y, x squared plus y squared. Plus, I'm going to do lambda times x plus y minus 10. So I'll get lambda x plus lambda y minus 10 lambda. Okay. So I've got this. And now I'm going to find my partials, fx, fy, f lambda. Okay. Now, I know partials were technically in the last chapter, but we do sometimes build on skills that we've used before. That's why we did our derivatives and our integrals review at the beginning, because sometimes we're going to need derivatives and sometimes we'll need integrals. I know we just came off of a super integral heavy chapter, but now we're kind of getting back into the realm of derivatives for a little bit. Okay. So derivative of x squared is 2x. Derivative of y squared is 0. Derivative of lambda x is plus lambda, and the rest of this also goes to 0. And I want to set that equal to 0. My fy, okay, x squared goes to 0. I have 2y plus lambda x goes to 0, negative 10 lambda goes to 0, and I'm just left with the derivative of lambda y, which is lambda. And I can't forget my f lambda partial. So I get 0, 0, and then I get x plus y minus 10. Okay. So we found our functions, f of x, y, g of x, y. We've created the equation with our Lagrange multipliers. And we found our partials with respect to each letter in our Lagrange multiplier. Now we are going to go and do what might be all of our least favorite steps, which is solve for the xy lambda using algebra. Okay, so let's write that in. I'm going to solve for x, y, and lambda with algebra. Okay, so I have, I have 2x plus lambda equals 0. And this is the same thing as saying 2x equals negative lambda, which is the same as saying x equals negative lambda over 2. Okay, so I've taken my fx equation and I've just gotten the x all by itself. And now I'm going to do the same thing with the fy equation. So 2 y plus lambda equals 0. 2y equals negative lambda, and y equals negative lambda over 2. Now, what this means is everywhere I see an x, I can replace it with negative lambda over 2. And everywhere I see a y, I can replace that with negative lambda over 2. Okay? So let me grab my f lambda equation. X plus y minus 10 equals 0. And now I'm going to make those substitutions. All right, negative lambda over 2 in for the x, negative lambda over 2 in for the y. And I'm going to be really careful about my signs. Okay. And this gives me a negative lambda equals negative 10, and then I get lambda, equals a positive 10, and lambda equals negative 10. All right. Now, once we find our lambda, we can plug it back in to find our x, and we can plug it back in to find our y. Okay. So x is going to be negative 10 over 2, which is 5. And y is going to be negative 10 over 2, which is also equal to 5. Okay, so in this point, or in this question, the x value is 5, the y value is 5, all right? It's okay for them to be the same value. But what we have now here is our critical point. We have a place where that derivative equals 0. And so in order to get the smallest value for f of x, y, we need to have x equals 5 and y equals 5. Okay? So I hope without all the other words, this was a nice way to kind of summarize that process. But again, I want to draw your attention to like, this is the part that's step 4. You got to think more critically about like, okay, what techniques might be useful here? Okay. All right, well, we got one more example left in this video, and then we'll take a quick break and I'll record the other video that is optional. Okay, so we're trying to keep the algebra to minimum here. And then in our last example, we'll kind of go off the rails and go a little wild with our algebra, but we'll keep it a little bit more put together for this last example. So the Cobb-Douglas production function for a new product is given by this function. N of x, y equals 16x to the 0.25, y to the 0.75. And x is the number of units of labor, and y is the number of units of capital. Now, they also tell us that the labor costs 50 and capital cost 100. And if they budget $500,000 for the production, they want to know how much of the amount should be allocated between labor and capital so that we have maximum production. Okay, this is a pretty classic business question where they really want to look at, like, you got a lot of things that go towards like the amount of production that you can make. Labor and capital, I think, are two of the most common ones and maybe are like pretty straightforward. But if we were adding another variable, there might be other things to consider, and we could use this method of Lagrange multipliers to solve that as well. Okay. But let's start the same way we've done all the other ones. Okay, we're going to find our f of xy and our and our g of xy. And we really want to remember that that g of xy has to equal 0. Okay, so in this case, our f of xy, the one we want to maximize is the production function. So that is the 16 x to the 0.25, y to the 0.75. Okay. Now, what is our g of xy? Well, they kind of tell us here that each unit of labor cost $50. That's the same as saying 50 times x. Okay. And each unit of capital costs $100. That's the same thing as saying plus 100 y. And all of that should equal 500,000, because that's how much they budgeted for the production of this project. So you could write 50x plus 100y equals 500,000, but remember, we want it to equal 0, so I'm going to subtract that 500,000 to the other side so that I can make it equal to 0. Okay. All right. From here, we're going to find our f of x, y, lambda. All right, here we go. F of x, y, lambda equals my f of x. So 16x to the 0.25, y to the 0.75. All right, plus, I'm going to go ahead and just take lambda and multiply it by everything in my g of x. Okay. So plus 50 lambda x plus 100 lambda y minus 500,000 lambda. All right, now that we've got our equation, we're going to find our 3 partials. And if you're feeling a little rusty on the partials, go back and watch some of the previous lecture videos. That's the nice thing about the online courses. You can go back and watch those recordings if you feel a little stuck, okay? All right, let's find our fx. Looks like I got to use the power rule. So 16 times 0.25, x to the negative 0.75, y to the 0.75 is still there, plus 50 lambda. And I think all the other terms go to 0. Fy is going to be similar, 16x to the 0.25, all constants, times 0.7y to the negative 0.25, plus 100 lambda equals 0. And last but not least, we have our f lambda, which will go 0, 50x plus 100y minus 500,000. Now, some of you might have noticed that this f lambda is the same as our g of xy, right? Let me just shrink this a little bit. Look at this. Our g of xy is the same as our f lambda, okay? So if you are like, well, I don't want to find f lambda because I know it's the same as g of xy, you can just go ahead and write g of xy. That's fine. But just keep in mind it has to equal 0, okay? All right, so we found all these things. Now for that step 4, we got to do a bunch of algebra and see what happens, okay? So solve for x, y, and lambda with algebra. Okay. All right, let's see what we got, all right? Now I'm going to clean up my fx a little bit, and if I multiply things out, I get 4x to the negative 0.75, y to the 0.75, plus 50 lambda equals 0. And what this allows me to do is to solve for lambda, okay? Now it's going to take a little bit more algebra than some of the other ones that we've had, but let's kind of start by moving this to the right-hand side. So I'm going to get 50 lambda equals negative 4x to the negative 0.75, y to the 0.75. And now I'm going to divide by 50 to get the lambda by itself. Negative 4x to the negative 0.75, y to the 0.75 over 50, okay? And I'm going to do the same thing for my fy. So when I multiply out all the things I need, I get 12x to the 0.25, y to the negative 0.25 plus 100 lambda equals 100. And just like I solved for the lambda up here by like subtracting this term to the right-hand side, I'm going to do something similar where now I take this term and I subtract it to the other side. And so that should get me 100 lambda equals 12x to the 0.25, y to the negative 0.25, and I'm going to divide by 100. And so I'll get 12x to the 0.25, y to the negative 0.25 over 100. Now, all of this is pretty gross, but let me show you something kind of cool. What we've done here is we found lambda and we found lambda. So what this means is this way of saying lambda has to be equal to this way of saying lambda, right? They're both equal to lambda, so the one in the green has to equal the one in the blue. And so let's write that as our next line. Negative 4x to the negative 0.75, y to the 0.75 over 50 equals 12x to the 0.25, y to the negative 0.25 over 100. And I'm going to go ahead and cross multiply here, okay? This is a time when I can use cross multiplication because I have the equal sign in between two fractions. So that's going to give me negative 400 x to the negative 0.75, y to the 0.75 equals, let's see, 12 times 50 is 600 x to the 0.25, y to the negative 0.25. And now I'm going to go ahead and move my y term to the left-hand side, and I'm going to move my x term to the right-hand side, okay? So what that's going to give me is negative 400 y to the 0.75 divided by y to the negative 0.25 equals 600 x to the 0.25 over x to the negative 0.75, right? So I can divide them, and now I can take care of my exponent. So when I'm dividing y, and they have the same base, the y, but they have different exponents, I actually subtract them. So I'm going to take 7.75 and I'm going to subtract negative 0.25. That gives me power of 1. So this is just negative 400y. If I do the same thing on the right-hand side, I'm going to have 0.25 minus negative 0.75 will give me 600 to the power of, or 600x to the power of 1, okay? So even though there were sort of these weird, gross, like decimals happening, at the end, we were able to get that exponent of 1, and that's actually going to be, we're like pretty close to being done, okay? So it doesn't really matter which variable you solve for, but I'm going to go ahead and solve for my y, and I think I've dropped a sign somewhere here. I did. So sorry, folks. This is a negative 12, negative, negative. This should be a negative 600. Sorry about that. But if I solve for y now, I'll get y equals 1.5x, okay? Whew. Now we'll take y equals 1.5x and we'll plug it into our f lambda. And that should be enough to get us to a value for x and then a value for y, okay? All right, so we get 50x plus 100y, which is now 1.5x minus 500,000 equals 0. And so this gives me 50 plus 150. So that's 200x equals 500,000. And if I divide by my 2, I should get x equals 2,500. Okay. And that x is measuring the units of labor. All right. And now that we've got an x value, we can plug it back into y equals 1.5x and we get our y value, okay? So y equals 1.5 times x, and that gives you 3,750 units of capital, okay? Now, let's make sure we've answered this question, okay? It says how much of that amount should be allocated between labor and capital, okay? Well, we have 2,500 units of labor and 3,750 units of capital. But look at this last part. It says, what is the maximum number of units that can be produced? What does that mean? We need to plug everything back into that Cobb-Douglas formula to give us the amount of units produced, okay? So I'll leave the calculations up to you, but essentially, if you plug in 2,500 for X and 3,750 in for your Y, you should end up with 54,216 units of product. Okay. And I believe on some of your online homework, they do ask you to find the units of product at the end. So make sure you answer like all the parts to the question. Okay. So let me get this all on one page for you there. And that brings us to the end of the mandatory part of the lesson. So I'm going to stop our video here.